Has it ever happened with you that you're trying to make a payment on your Amazon app for buying something and it suddenly asks for your girlfriend's zodiac sign? It didn't, right? That's all thanks to the Liskov Substitution Principle. Hello engineers, welcome back. In this video, we're going to tackle the third principle in Solid, which is the Liskov Substitution Principle. I hope you're ready. Let's get started. So as per the definition, objects of a subclass can replace objects of a parent class without affecting the functionality of the system. Now, I know that doesn't make much sense, but let's try to understand this principle with some examples. Imagine we are building a parking management system, and this system should allow for parking of all types of cars. It can allow a sports car, it can allow a hatchback or a small car or a big car. The parking system should not misbehave or should not change its behavior depending on the type of the car. It cannot suddenly say to a sports car that you're too fast, or it cannot suddenly say to a hatchback that you're too small. It should behave the same way for all types of cars, right? That's what the principle is all about. Now this principle will be more clear if we look at some code examples, right? So let's get into code and try to understand this principle in detail. So I've created a new folder called the Liskov Substitution Principle, and as always we have two files. One is the concept file and another is the use case file. In the concept file we will try to understand the principle using a fun example, and in the use case file we will try to look at a real world use case, right? So let's see. So let's say we have a pizza delivery class, right? And it is having one method, deliver pizza, and it has its own implementation, delivering pizza at your doorstep, which is a simple print, right? And let's say there are two subclasses, regular delivery and drone delivery, which are inheriting from the main pizza delivery parent class and implementing their own deliver pizza methods. So even though both the subclasses are implementing the deliver pizza method, their behavior is slightly different. So let's have a look. For the parent class, when we call the deliver pizza method, it is doing a simple cout. And the regular delivery also is doing a simple cout. No problem. But the drone delivery method is doing something different. It is asking for the input from the user. Is the customer ready to pick up at the door? If it is ready, then drone is lowering the pizza to your doorstep. Otherwise, it is asking the user to come to the door to collect the pizza. Now this is a strange behavior. So when we try to use this subclass, wherever we were using these classes, regular and pizza delivery, the behavior has changed. Now this is a violation of the Liskov substitution principle. Why? Let's see what happens when we run this code. So if you can see here, we are calling two methods, one with a regular delivery and another with a drone delivery. The regular delivery method has finished pizza delivered by your friendly driver at your doorstep, so no surprises there. But when we are doing a drone delivery, it is suddenly asking for user input, which is not an expected behavior considering the base class, which was doing a simple cout, right? So this is a violation of the Liskov substitution principle, because wherever we are using the delivery service, which is a pizza delivery service, right? We should be able to use both the base class and the subclasses. And all of them should behave in a similar way. There should not be any side effects, there should not be any misbehavior or unexpected twists during the implementation. So this is a violation of the Liskov substitution principle. So how do we fix it? Let's have a look. So this is the fixed version of the same implementation. So we have the pizza delivery, which did not change. We have the original deliver pizza method, and then regular delivery is also the same. But now drone delivery is also doing a simple cout, which is what we need. Now when I run this code, we should not see any surprises. See, pizza delivered at your doorstep, drone is carefully lowering to your doorstep. So both the deliveries have successfully completed and there are no surprises. So this is a simple fix. But you might say, hey Uday, but what if really the drone delivery guy requires a user input? How do we handle that case? So let's have a look at that in our use case file. So let's first look at the violated version and then we'll look at the fixed version. So let's say we are implementing a payment gateway. We first have a base class, which is a payment class, which is doing a simple cout for process payment. And then we have two subclasses, credit card and debit card, which are doing an implementation of the same process payment method, but they are slightly misbehaving. So just like in the pizza case, this time the debit card method is asking for a user PIN. Enter PIN to process debit card payment. Now this is a misbehavior with respect to the base class, which was doing a simple cout, right? So this is a violation of the Liskov substitution principle. And as you would expect, when I run this file, the credit card payment will go through smoothly, but the debit card payment will ask for user input and the program will stop execution, right? Which is a misbehavior. So let's run this code and see. So as you can see, credit card payment has processed, but for debit card payment, it is waiting for user input. Only when I give the correct PIN, it will complete the process, right? Otherwise, it is waiting for user input, and that is not an expected behavior. And this kind of implementation is a violation of the Liskov substitution principle. So how do we fix it? Now let's take a look at this implementation. First, we have the same payment base class, which is doing a simple cout. And we have the credit card, which is also doing a simple cout. No problems here. But for debit card, we require a PIN. So how do we ensure that we take a PIN and use it and not violate the Liskov substitution principle? So what we do is, one of the approaches we can take is, we can create a constructor that takes in a PIN with the same name, debit card. And when we are creating a debit card object, we can pass in the PIN. We can see two implementations here. One is with the correct PIN, one is with an incorrect PIN. And when we go back to the process payment method, we are only checking whether the PIN is valid or not. This is still okay. We can do any kind of passive work inside the process payment method as long as it is not deviating from the original payment method class, right? So this is a simple cout, this is a simple cout, and when we process this, we get two couts. Either we get this one or we get this one, which is what is an expected behavior from this process payment method. And because we have implemented it this way, we have successfully fixed the violation of the Liskov substitution principle. Now if I run this code, there should not be any surprises. See, first time it went to a credit card payment, second time it went to the debit card payment with correct PIN, and then third time it went with invalid PIN. These are the three calls we made for our execution, first with a credit card, then with a correct PIN, and then with an incorrect PIN. So all three of them have processed in the similar way without any misbehaviors. So this is a good example of a Liskov substitution principle. So I hope you've understood the implementation and the reasoning behind Liskov substitution principle. If you have any questions, definitely ask me. Don't forget to leave a like if you found this helpful. Do comment if you have any questions or suggestions. Don't forget to subscribe to the channel if you haven't done already. Thank you so much for watching, guys. In the next video, we'll look at the fourth principle, which is the interface segregation principle. Thank you so much for watching. I will see you in the next one. Cheers.